Hello, and welcome back to General Chemistry 2. My name is Daniel, and in this video we're going to be doing a continuation of our study of chemical kinetics. We're going to be looking primarily at what's called reaction mechanisms. So all the reactions we'll be considering can actually occur in multiple steps. So we can derive rate laws and look at the kinetic behavior of these reactions in terms of their elementary steps, the ones that occur to give us our net reaction. Later in the video, we'll be looking at the energetics and some thermodynamics of how reactions occur. We'll be looking at things involving collisions between molecules, how the energy of collisions and the orientation of collisions affects how many effective reactions are going to occur. So, like I said, we're going to start off with reaction mechanisms. So, chemical reactions often involve multiple steps and the creation of the species called intermediates in between until we get to the final reaction. For example, if we look down here, our net reaction, this top one, is NO2 plus CO forms NO plus CO2. But we can split this into two steps. So the first step is the combination of two NO2 molecules. The second step is the reaction of NO3 and CO. Now what we see here is, let's look at this NO3. This NO3 is produced in reaction 1 and then used up in reaction 2. So NO3 is what's known as an intermediate species. We also see that it's not in the net reaction. That would be just, from adding those two up anyway. So one of the big things about intermediates is that when we look at rate laws based on intermediates, we can't have an intermediate in our rate law for a reaction. So what we're going to be predominantly doing with our reaction mechanisms is looking for different ways to replace NO3 and other intermediates in our rate laws with other terms. And we'll see how to do that in the next upcoming slides. So when we're looking at reaction mechanisms, the first rule is that the sum of the elementary steps, that's each of these little steps before the net reaction, each of them has to add up to the full reaction itself. And then second, there's usually a rate determining, or what's called slow step, which occurs more slowly than the other steps, and hence it's what's known as a rate determining step. We're going to write the rate law for a reaction based on that rate determining step. So let's look back at this. We have this reaction here. Let's add it up and see what it gives us. We get rid of NO3 on both sides, and NO2 on both sides, and we're left with our net reaction, which matches the one we had in the previous slide. Oops. Alright, and then we see that step 1 is what's called our slow step. So the rate for this whole reaction here is going to be based on our slow step. The rate then is just equal to K1, that's the rate constant for equation 1, times NO2 squared. When we're doing the rate laws for elementary steps, we're going to be doing it based on what's known as the molecularity. So we have unimolecularity, bimolecularity, and what's called pteromolecularity. So that's just talking about what the rate law is going to be for various elementary steps. For example, if we have just an elementary step of a decomposition just from reactant A to its products, that's going to have a rate law of K times A. If we have two A's, like in the previous one, that's bimolecular, so that's going to have a rate law order of 2. It's going to be Ka squared. If we have the combination of two different reactants, A and B, that would have the rate law of K times A times B. Now note that these are only for the elementary steps, not the full reaction. We have to go look through the elementary steps and work through them in order to determine the rate law for the full reaction. And we'll see how to do that in one of the upcoming slides. So a common reaction mechanism that we see is one of a fast equilibrium step. That means something like this. If we're going from A to B, equilibrium is going to look like this. There's going to be a forward reaction from A to B and a backwards reaction from B to A. And these have their respective rate constants, K1, and then the reverse is usually some kind of negative subscript. what we can do is we can use the equilibrium of this reversible step in order to determine rate law for mechanisms with intermediate in the slow step. Let me show you what I mean. So let's look at this problem. We want to determine the rate law for this reaction given the proposed mechanism. So we have a slow step on the bottom, and we have this fast equilibrium step on top. So we know that the rate's based on our slow step. So we can write that the rate is going to be equal to K2 times the concentration of O times the concentration of O3. However, what we'll note is that O is an intermediate. So that means we can't have it in our final rate law for this up here because it's not present there, and it's also used and consumed. So what we have to do is we have to find a new expression for just the oxygen atom. And we can do that using our fast equilibrium step. We can say that the forward reaction is going to equal the reverse reaction in terms of kinetics. So what that turns into then is K1 times the concentration of O3 is going to equal K-1, the reverse reaction, times its molecularity, which is O2 times O. Okay, so we just took this and made the forward step equal to the reverse step in terms of kinetics, and now we have this expression. We can use this expression to give us a new term for oxygen atom that involves everything that's in our net reaction. So if we divide both sides like so, that's going to give us that the concentration of oxygen can be rewritten as K1 over K-1 O3 over O2. So now what we can do is we can take this new term for the oxygen atom and plug it in to our initial rate law that came from our slow step. That's going to be one of the most important steps we do when we're doing these kinds of reaction mechanisms. We're going to find a new expression for an intermediate based on non-intermediate species and plug it back in to the rate law from the slow step, the rate determining step. So that would look like so. The rate is going to equal K2 times K1 over K-1 O3 squared over O2. So that's our full rate law. We can reduce all of these rate constants by just saying that some K equals K2 K1 over K-1, and then so finally we get a net rate law of O3 squared over O2. Okay? So all we did here is we used the we determined the rate law from the slow step, found there was an intermediate in it, so then we used the reversible fast equilibrium step, said that the forward reaction equaled the reverse reaction kinetically, and we used that to give us a new expression for our intermediate that we plugged back into the slow step, into the rate law from the slow step, and then just solved everything from there. And we get our final rate law down here. Okay, so that's one common problem we asked about. Let's look at another. See if you can pause the video and try out this one. What we're asking here is that we're saying the following reaction has this rate law that's been experimentally determined. We want to know if we get the same rate law from this proposed mechanism. You can propose multiple mechanisms, but if they don't match the experimental data, they're not, very good mechanisms, obviously. So see what rate law you get from these three steps here. Take a moment to try that. Okay, so let's take a look. We know that our slow step is reaction 2, so we can initially write that the rate is simply going to be equal to K2 times the concentration of N2O2. That's just from the molecularity of that step. What we see, though, is that N2O2 is an intermediate species. It's produced in reaction 1, but used up in reaction 2. So what we have to do then is write a new expression for N2O2. So what we're going to do is we're going to take this fast equilibrium step and set the forward and reverse equal to one another.